the object here is temporarily stationary, equilibrium. Okay, the net force is 0, and when we pull it down from equilibrium and release it gently, it starts oscillating up and down, and this little vibration oscillation is called simple harmonic oscillation. When increasing the amplitude like this, the oscillation become more unstable. There are more like noise, some disturbance in other directions, rather than only oscillating up and down in a small amplitude. Simple oscillation simulation. If we have a pendulum, spring pendulum like this, and attach to it a pen, and behind it there's a roll, paper or cloth, that's roll, we'll see the pattern like this way, sinusoidal wave. Okay? Yeah. Sinusoidal wave. This is how the displacement of the oscillator, the object, changes with time, sinusoidally, described by a psi function. Okay? So simple harmonic motion has two main properties. Firstly, its displacement is described by a psi function. Displacement x will be described as the amplitude times sine of omega t. Okay, omega in this equation is called angular frequency. Angular frequency, and it is equal to 2 pi of the normal frequency. Frequency f is the number of oscillation in 1 second. Okay. Yeah. The second condition for simple harmonic motion, actually not condition, but property, is nature, is that it is governed by the force, the resultant force, called restoring force. Restoring resultant force. Restoring force means that the force, the direction of the force, is always poised toward the equilibrium position. And the second property is that the magnitude of the force is proportional to the displacement. Okay, so the force is written as minus k times displacement x. It is similar to the elastic force, the spring. Okay, similar to Hooke's law, elastic force, but k here is generally not the spring constant, but can be a constant, depends on the type of oscillation. In the previous experiment of the spring pendulum like this, the restoring force is the sum of the weight of this object and the elastic force of the spring, the sum of those two forces, not just the elastic force. Okay, so basically the resultant force is the restoring force. When we double increase the displacement by 2 times, the force resultant will be 2 times greater. This is an example of simple harmonic. A spring pendulum and an object can move smoothly on a very smooth surface, and this is a simple harmonic oscillation. Okay, very low friction.
So okay. The simple harmonic motion doesn't stop?
Yes, almost never. The one more condition is that the loss of energy is tiny, it's negligible, so the oscillation can maintain for a very long time. Okay, yeah. Little loss of energy. This diagram illustrates different position of the oscillator. Initially, the time 0, when we start the clock to measure the time, it is at the highest displacement, which means the amplitude on the right. And then after 1/4 period, this object returns to the equilibrium position. After half period, it is exactly on the opposite side with the greatest displacement, meaning the amplitude, but now negative amplitude on the other side. Okay, 1 period is the time for a complete oscillation from this initial position to the left and then return to this position again. That total time is the period. Okay, this is the graph of acceleration and displacement. Okay, which I will talk later. I will find the graph of velocity and displacement first. Okay, here it is. The two graphs of velocity and displacement. So basically, derivative describe the rate of change, how fast a function, a variable changes with time. For example, we have a function describing the position x of an object, okay, like x equal vt. T is time, v is the speed, okay. Derivative of x, or another name called differentiation, dx over dt, or x prime derivative is v, either speed, meaning how fast the position of the object changes with time. So we have one property of the simple harmonic oscillation is that the displacement here is a sinusoidal function, a psi function, omega t, okay? And when we take the derivative of that function, x equal a times sine omega t, we will get the velocity, which is derivative of displacement x. It will be omega a times cosine omega t. The reason why we have this a very long explanation, okay, very long why the derivative of sine cos, but just take this equation for now. We come back to explanation later.